И сейчас я, прежде чем предоставить слово профессору Ламберти, я хочу предоставить слово профессору Солдатову Александру Владимировичу. Он тоже наш постоянный участник. Мы знаем прекрасно и его достижения, достижения его молодого коллектива, как он умудряется, он может это рассказать. А сейчас вот у них совместный большой мегапроект. Пожалуйста, Александр Владимирович, вам слово.
Спасибо. Значит, я в преддверии выступления Ламберти, который просил извиниться, но русский он еще не освоил, достаточно, чтобы говорить, так, в обиходе он может несколько слов сказать. Вот. И что я хочу сказать. Во-первых, действительно информационные технологии вошли в нашу жизнь. Ну, к физикам они вошли очень давно, у нас даже науки называются, нет физических наук, если вы знаете, вот, по степеням, есть только физико-математические науки, то есть физику и математику уже давно не делят. Вот, ну и сейчас, вот, говоря несколько слов о профессоре Ламберти, я что хочу сказать, я тоже сейчас воспользовался информационной технологией, взял вот, выпущенный компании Apple девайс, зашел на сайт нашей лаборатории, где есть профиль Ламберти, и посмотрел сегодняшние данные его по Web of Science. Значит, индекс Хирша 63, число цитирований 12456. Вот, и, ну, и основной рецепт таких достижений, он достаточно простой. Ну, его, может быть, не понять в интернете, но вот мы сегодня ехали в машине, и он сказал, говорит, я встал в 4 утра, чтобы дошлифовать презентацию. Вот, так что работа. И, пожалуйста, и еще 30 секунд вот о нашем совместном проекте. Проект достаточно большой, поэтому называется мегапроект по 220-му постановлению привлечения ведущих зарубежных ученых, но он тоже состоит по сути из 3 частей. Это создание лаборатории нового типа, от компьютерного моделирования до синтеза и характеризации. То есть у нас, грубо говоря, треть проекта это химия, синтез, треть проекта это физические методы характеризации, но треть проекта это методы компьютерного моделирования. И вот именно о том, насколько это важно для физики и химии, для material science, которая мы представляем, профессор Ламберти will talk us about the importance of computer technologies.
Спасибо большое, Александр Владимирович. Уважаемые коллеги, доброе утро. And now I have to switch in English because my vocabulary in Russian is almost finished there. Tomorrow we try to learn a 5th one. Okay, so it has been told to me that there will be a quite broad audience here. So the first part of my talk will be quite general, quite didactic and a little bit historical on the role of computer science in material science. So I apologize for the people that work as solid-state physicists or quantum chemists, because this will be quite boring for them, but I hope it will be of some interest for the remaining part of the audience. Well, I skip an important part, and so these are complex experiments, and in order at the synchrotron or at free electron lasers and so on, and in order to make the experiment possible, computers are fundamental. I will not speak about this in my talk. I will speak on how computer simulation will help us in understanding and in the interpretation of the experimental data. But this first part is also as important as the first, of course, because if I'm not able to collect good quality data, then I cannot start with understanding how my materials work. And so this is the two sides of the medal. One is making high-level experiments, and the other one is understand what is behind. And in our mega grant project, we are running on both sides. So let's take it a little bit historically. I think that the beginning of the use of computer was in the early 50s when these guys in the US started to use a machine in Los Alamos laboratories to run the first Metropolis Monte Carlo simulations. That way. Then everybody knows, of course, here the Moore laws. The evolution of hardware in computer is impressively increasing, and so computational tasks that may be out of our possibilities today will not be in such condition in the future, may be reachable in the early future. And an important thing on an economical point of view, the cost per computation becomes more and more competitive. And so we are running two opposite directions. Normally, high-level laboratory experiments are most and most expensive. If you think the cost of high-quality transmission electron microscopy nowadays, we are running about 2 billion euros. If we want to collect high-quality X-ray diffraction data, we need something like 200,000–300,000 euros. The price of this instrument is always rising up, but this is not true from the price of computation. So it is clear that it will be more and more interesting to have high-level computation potentialities in labs that run material science experiments. Then, of course, and again we can see that our final goal is to understand the physico-chemical properties of our materials, and we can run on a parallel ground. We can make experiment, we can make computationals, and when we make an experiment we have to make choices. We can make NMR, infrared, X-ray diffraction, X-ray absorption, X-ray emission experiments, depending on what you are looking for. On the other hand, also choices are needed on the computation, because we can run molecular simulation, we can run ab initio calculation, we can run something in between semi-empirical, and we can we can see the response of our materials by changing the environmental condition. We can change the temperature, we can change the pressure, we can put our material inside the material, a magnetic field, for instance, and see how the response of the material are on an experimental point of view. But this can also be done on a quantum mechanic approach, because we can add external electric field or magnetic field and so on. But at the end, we have to reach a joint picture combining experiments and theory. Now, in order to understand a material from ab initio data, basically we have to solve the Schrödinger equation, which is a very complex equation that takes into account the coordinates of a system of electrons and nuclei. And so we have two terms of kinetic energy of electrons and neutrons and nuclei, and then we have three different potential terms, which are the repulsive interaction between electrons and between nuclei and nuclei, and we are the attractive potential between electron and nuclei, and this term is what takes the materials together. Then, of course, this equation is almost unsolvable, and then two guys helped us a little bit. These guys are Born and Oppenheimer, and as the mass of the nuclei is more than three orders of magnitude heavier than the mass of electron, and as in the kinetic term in quantum mechanics the mass is on the denominator, this term is at least 10 to the minus 3 times this term. And so in first approximation we can neglect this term, and this has a big consequence, because if we neglect the nuclei motion, this means that the nuclei do not move anymore, so they are in a fixed position, and if they are in a fixed position, then the very complex internuclear potential becomes a constant. So it can split out of all integrals, and I can only run the Schrödinger equation on this part, adding at the end the repulsive energy of the nuclei, which is a constant. And this makes things much more easy to handle. Then, of course, still it is a complex problem, and we need, in the first approximation, to run in a single electron approximation to introduce the Slater determinants, and this is a big problem. In order to bypass the problem of single electron approximation, there are more complex approaches like MP models of coupled clusters, but these will be, as we will see, quite time consuming. We have to take into consideration that the single electron Hartree-Fock approximation takes into account almost of the energy of the system, and we basically are just missing the dispersive interaction, which so are very important for weak interaction in particular cases. Well, let's now speak about computer time. So this, if we run a very complex biological molecule at Hartree-Fock level of theory, we will need almost the same CPU times that are running at MP2 level a very small molecule. So this level of theory is much better. We have much more accurate results, but it is more time demanding. And you compare the size. Here, the same CPU times allow us to treat a very huge molecule, in this case, a much smaller molecule. And if we go the coupled cluster, I mean, the size of the system that can be simulated with comparable CPU times is even smaller. So one has to do choices depending on the size of the system, how complex and sophisticated can be the level of theory that we are working with. Then a big improvement comes when basically we realize that in order to know the system, it is not really needed to know the wave function. And the wave function, keep in mind, this is a complex function defined in all points of the space that tell you. But the important thing is to know it will be sufficient to know the electron density. And this is much easier because the electron density is no longer a complex function, it's a real function, it's a real positive function of all points of the space. So it will be much easier, and basically this is the beginning of the so-called DFT, density functional theory, that developed in the early 60s, and that nowadays becomes the more popular way of making computational of material science systems. And why this, but this can be understood in the next slide, basically because it is very economical on the CPU time. So here we have on the columns represent increasing level of theory, so Hartree-Fock, Bitralib, which is an hybrid DFT Hartree-Fock approach, and then we have two increasing complexity MP approaches, and then we have the coupled cluster. So when we move from left to right, we are increasing the level of theory, being able to be more and more accurate, and conversely the rows are the so-called basis set, and the basis set is which define how accurate the accuracy in the definition of the atomic wave function, let's say. So here each atoms moving from top to bottom is defined with a much more complete his wave function is defined in a much more complete way of working. And we see that basically the scaling of this DFT-based system by increasing the complexity of the basis set is much more advanced, much more interesting than the other systems. In this case, this scaling is almost impossible to be affordable in normal computers. Okay, then of course we say we have to make choices. If the molecule, if the system that we are working with is small, then we can run full ab initio. This means that this will be a full electron approach. All electrons in the system will be taken into account. If the system is more complex and we have some heavy elements, and heavy elements have a lot of electrons, so this means they are very huge on a computational point of view, then we can use so-called semi-empirical approach. This means that the inner core electrons will not be treated as on a quantum mechanical point of view. So we will consider the nucleus plus the inner electron, and the inner electron, those that almost do not contribute to the chemical bond, they are treated in a classical way with self-potentials. And then, of course, if we have a very huge molecule, then we are forced still to run in a classical approach using mechanical dynamics. But what happens if our system is a solid? If the number of molecules is an Avogadro number, it is the order of magnitude of an Avogadro number, then, of course, in principle, all the system, even with this increase of the computer speed, even if with all these approximations, are apparently not affordable. Well, here we have two approaches. If the system is amorphous or non-periodic, then basically what we can do is to run an approximation on the size using the so-called onium approach. Onium is a vegetable, it's a look. So you say that this look has different spheres around them, and by increasing the spheres we can decrease the level of theory. So the inner shell will be calculated at high level of energy of approximation, and then the external shield, the external sphere will be calculated at a lower level of approximation. Of course, if the system is periodic, then we are lucky because the Bloch theorem helps us, and then we can limit the calculation actually on the unit cell, actually on the symmetric unit of the unit cell, and then using the symmetry properties to propagate the knowledge of the wave function on the whole system. This example deals with metal-organic frameworks, which are one of the three classes of material that are investigated in the mega grant that is running here at SFEDU. This name is called CPO27 nickel, and basically this is a very complex system. Here, these are empty spaces. So if we pump, these are molecules inside, but if we make the vacuum, you will have these channels that will become free. How is this material done? So this is crystalline, irregular, so we can run periodic simulation. Okay, it can be constructed with several different divalent cations. We focus basically on the nickel one, and you can imagine that we have. So this material. Imagine that you are making the construction of a building, and you use pillars, and these pillars are nickel oxygen nickel oxygen nickel oxygen chains that run along this direction, and you have 6 pillars of them: 1, 2, 3, 4, 5, and 6. Okay, and then you need walls, and these are, let's say, the inorganic black bones. And then in order to construct the walls, you use organic ligands. And in this way, you are building up a three-dimensional structure that has one-dimensional channels, and these channels can host molecules. And you can change the dimension of this channel simply choosing a larger ligand molecule. Imagine that we put here the second benzene rings and here the decarboxylate units. We can build exactly the same structure, simply slightly bigger. And so we can play with the dimensions. And this gives us a lot of flexibility also in the application. Keep in mind that this material has an impressive surface area. So we have surface area of larger than 1,000 square meters per gram. This means that the single gram of this material has a surface area which is larger than several football fields. And this is because we don't have just only the external surface area, but we have also the internal surface area. So this material very important for absorption property, for gas separation, and for catalysis. Yes. And then of course we run ab initio calculation on this system, because this is a crystal, this is periodic, so we can do the job. The first thing is we can compute the stability of the structure. And we can check the experimental versus the theoretical, the experimental versus the theoretical lattice dimensions, volume cell, and so on. And we see that, for instance, the computer simulation are very able to take into account the change of volume that happens when I change the nickel 2 plus with magnesium 2 plus. Then then we can we have a spectroscopy that we use a lot, and the single is X-ray absorption spectroscopy. I will not enter into the details, but basically we obtain this kind of experimental signal, which is in Kerr space an oscillatory behavior. But if we make the Fourier transform of this, we get something like the radial distribution of distances around the nickel atoms. And so this first peak basically is due to the first shell oxygen. So this peak is the convolutes is the red one, and is the contribution of these 5 oxygens. And then at larger distances we have this peak here, the blue one, which is due to the 2 nickel distances along the chain. And then we still have a significant contribution, which is the green one here, which is the same contribution due to the second neighbor's nickel atoms along the chain. And then these are, the quantitative result of this analysis. I will just go very fast on this, just simply see that this distance is changed when we remove water molecule on nickel. And an important thing, so this nickel is 5-4 coordinated. If it is 5-4 coordinated, this means that this nickel has what chemistry called a coordination vacancy. This means that if I send some molecule here, this molecule can be coordinated on nickel side. And I can do this for NO, so this can catch NO. This is the infrared and Raman stretching frequency of NO adsorbed on this nickel. I can, and this is the calorimetry, so we have 90 kilojoule per mole of absorption enthalpy, and we can see what happens with extra. So we see the additional, this is the contribution of the NO molecule absorbed on nickel, and we have 1.85 of distance between the molecule and the nickel. We can do the same job for CO, carbon monoxide. We have a microcalorimetry result, so we can experimentally measure the heat of absorption, and we can compute the heat of absorption with different basis sets, and we see that basically experimentally we run between 58 and 54, which is more or less the result that we get with the most accuracy basis set. This is again the exhaust results with the contribution of the CO molecule, and then we have here, we can compute ab initio the absorption of a CO molecule there. The bonding distance this is in picometer, so it is 2.09 angstrom, and experimentally we have 2.9 angstrom. Experimentally we have 2.11. These can also absorb nitrogen. This is the results of nitrogen. This is a general trend of how the exhaust results change by changing the absorbed molecule. And here we will compare different molecules absorbed on these systems. These are the ab initio calculations of the interaction of water, NO, CO, nitrogen and CO2. This is just a graphical picture of the MOF. And we can measure with Raman and with different the vibration of the system, and of course we can use ab initio calculation to calculate a computed vibrational spectrum and compare this. And this is the results where on the left we have experiment and on the right we have theory. These are the different molecules that are plotted as a function of the enthalpy of absorption. So on the left, of course, this is the dehydrated material. Then you have the molecule with the weakest interaction, which is nitrogen. Then you have the molecule with the highest interaction with NO and water. And we see, and these are the calculations, and we see that basically we have an agreement, in fact, that if we use molecule with an increasing absorption enthalpy, the modification of the first shell, recently with the nickel and oxygen, is increasing, and then the same holds for the first shell nickel-nickel distances and the second shell nickel-nickel distances, while we obtain an opposite trend in the molecule to nickel distance. Of course, if the bonding energy is stronger, normally the absorbed molecule comes closer to the nickel center. Then I will finish with some unpublished results that have just been submitted to Journal of Chemical Theory and Computation, and this is a work done basically here in Rostov in collaboration. So these and there's two different departments, the Department of Physics and the Department of Mathematics. And then we have collaboration with colleagues in Germany in the free electron lasers, with colleagues in France, Italy, and myself. And these end us with simulation of Texanas. I never speak about simulation of Texanas before because this is one of the most time-consuming way of calculation, because we need to construct a very big cluster around the absorbing atom to get accurate results. This example is very clear. These are simulations obtained using bigger and bigger and bigger cluster. And you see that we still see differences. So this means that you really need to have a huge portion of solid in order to be able to reproduce correctly the sun spectrum. And this is very time demanding. And people here in SFEDU were able to work on this code and to increase tremendously the speed of calculation. So we need that on the big cluster we gain something with respect of the original code. We gain something close to 40 times faster code to obtain the same results. And also in terms of required RAM to store the calculated integrals, we gain a factor 2. So this is very important. And this allows us to apply this approach to a very complex system like СИТО-2015 in interaction with molecules. And keep in mind that a simulation like this in the normal code would have taken something in the order of 1 week of calculation on a good computer. Then if we gain a factor 40, this means that we have the answer in a fraction of that, which is big. And so this allows us very important things to do is to calculate the geometry of absorption, because in the past what was done, simply you take the ab initio calculation and then you fix this geometry like this. This is the nickel cation. This is the CO or the NO molecule, and you trust the ab initio calculation. You say, okay, the molecule is like this, and you run the simulation. You compare experimental and simulated. Now that we can improve the speed of this code, we can change the geometry and we can change the orientation of the molecule in order to check if the predicted one is really the good one. Compare the theory and the experiment. So here on the ordinate is the difference between, in the whole spectrum, between the experimental and the spectrum, the theoretical spectrum computed at different orientation. Here is the bounding angle. And so for CO molecule, which is the red squares, we see that we've got the minimum close to 180, so this means that the CO molecule is linearly absorbed on nickel 2+, and while for NO we have a band geometry with a maximum which is close to 100-something degrees. And so with this picture I thank you very much for your kind attention, and I will be glad to answer to some questions if there are.
Thank you very much. Thanks to you being urgent for these serious scientific results. Now maybe, может быть, вопросы, комментарии, пожалуйста, профессору Ламберти. Вот вы прикоснулись к очень действительно серьезному исследованию. May I ask
Of course, you're more than welcome.
About your project,
Yes.
Megagram. What the main results are you waiting from this project? Connected with computing, with theoretical research, maybe with supercomputer. What you're waiting from it?
So I'm waiting a lot because if you remove computer from our research, it will try to run a Formula 1 race with only 3 wheels. So you will not go very far. We are able now today to take very sophisticated, very complex experimental data, which is very nice. But in order to understand and to make a correct interpretation, we really need ab initio calculation. And when the system is complex, the technique is complex, then of course the computational time required is high. And so without computer, we can almost go no way nowadays.
Thank you. Thank you very much again.
My pleasure.